Day off in Kyoto, got bored at the temple, looked around at the 7-Eleven. The band took the speed train, went to the arcade.
In this last video, I want to talk about an application of the Chinese remainder theorem. But before I do that, I want to recall some things about ring homomorphisms from Dummit and Foote, and also from Conrad's notes, this document about standard definitions for rings that we talked about at the end of last quarter. So first, let me give this statement from Conrad. I'll put a link to exactly what statement and what document this is in the course summary of lectures page. Let's say that R and S are rings with identities. Let's say 1 not equal to 0. And phi from R to S is a ring homomorphism that sends the identity of R to the identity of S. Remember that that's actually part of Conrad's definition of what it means to be a ring homomorphism. Then, well, what happens when you look at where phi sends the units in R? Well, the units of R get sent to units in S. And if you take phi and you restrict it to the units, what you get is a group homomorphism between these two groups of units. So Dummit and Foote don't prove exactly this. They say something kind of close, which is exercise 17 in section 7.3. Let's take non-zero rings with identities, 1R and 1S, and let phi from R to S be a non-zero ring homomorphism. If you send the identity of R to something other than the identity of S, then you have to send it to a zero divisor in S. Okay? And if you do send the identity of R to the identity of S, then you're back in this situation up here, and U is a unit, then phi of U is a unit in S, and the inverse of phi of U is phi of U inverse. So the second part is close to this statement here. All right, so I'll tell you why I brought this back up in a second. It is not difficult at all to see that the units in a direct product of rings are the elements that have units in each component. So you can check that that's true, but it's pretty straightforward. Because the group operation, the multiplication operation in this direct product of rings is component-wise, you'll see why this is true. And in the case where all of your ideals, A1 up through AK, are pairwise comaximal, where you get this isomorphism between R mod the product of the ideals to the direct product R mod A1 cross R mod A2, and so on, it really does send the identity of the first ring, 1 plus A1 times AK, to the identity of the direct product, 1 mod A1, 1 mod A2, 1 mod AK. You can check that this statement really is true. And what Dummit and Foote say is that this isomorphism then gives an isomorphism of the group of units, R mod the product units, is isomorphic as a group to R mod A1 units cross 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 R mod AK units. This is true, but I don't think it's clear that this is true given what Dummit and Foote have already said, right? That if you have an isomorphism of rings that sends the identity of the first ring to the identity of the second ring, then it induces an isomorphism of the groups of units of these two rings. So I don't think that that's so clear given how this was presented in Dummit and Foote, but it's true, and you can check if you just look at what this group homomorphism is. In the particular case that phi is an isomorphism, you'll see that this is an isomorphism as well. But I spent a little while thinking about this and wanted to point it out that there really is something to think about here. So you should check that you really believe that this is true. Okay, so I'm going to pause and erase, and then we'll see an application of the Chinese remainder theorem and this statement about the units in the particular case that our ring is equal to Z. So let's see an application of the Chinese remainder theorem when our ring is equal to Z. Let's take a positive integer n with prime factorization, p1 to the alpha 1, p2 to the alpha 2 times pk to the alpha k. So each one of these alpha i's is greater than or equal to 1, and these p1 up through pk are distinct primes. Then z mod nz is isomorphic to the direct product of the rings z mod p1 to the alpha 1z cross cross cross, z mod pk to the alpha k z. So it really is important that these are isomorphic as rings. We already knew these were isomorphic as groups. For example, a finite abelian group is isomorphic to a direct product of its CLO P subgroups. So yeah. Okay, so this is a first application of the Chinese remainder theorem. I guess what I'm not saying here is that the ideals P1 to the alpha 1z up through like Pi to the alpha iz, that set of ideals, those are pairwise comaximal. Because what does it mean for mz and nz to be comaximal is that the GCD of m and n is 1. So now this statement comes directly from the Chinese remainder theorem. And given what we just said, this isomorphism of rings induces an isomorphism of the groups of units on both sides. So the units of z mod nz are isomorphic to a direct product of the units of z mod p1 to the alpha 1z, direct product, the units of z mod pk to the alpha kz. Now taking orders on both sides, how large is the group of units on the left is phi of n, the Euler phi function. How large is the group of units in z mod p1 to the alpha 1z? It's phi of p1 to the alpha 1. So this product of Euler phi functions is equal to phi of n. One way to say this is this function is weakly multiplicative. Okay, well, what are these values? It's easy to see that phi of p to the alpha is p to the alpha minus 1 times p minus 1. Because what are we counting? We're counting the number of k between 1 and p to the alpha so that the GCD of k and p to the alpha is 1. But what does it mean to be relatively prime to a prime power? It just means p does not divide k. So you can count the number of k that p does divide and throw those out. And this is the formula you get. Okay, so where are we now? We would like to understand z mod nz star, the units of z mod nz, as a direct product of cyclic groups. And we still don't know how to do that, but we do know that it's enough to understand z mod nz units in terms of a direct product of z mod p1 to the alpha 1z units. Like the prime power case is enough. So we need only understand what do the units of z mod p to the alpha z look like as a direct product of cyclic groups. And what do we know so far? So we have stated, and we used this last quarter quite a bit when we talked about automorphisms, that z mod pz star is cyclic. And we know that z mod nz star is not always cyclic. For example, z mod 8z star, or z mod 2 cubed z star, is isomorphic to z mod 2z cross z mod 2z. So this is not cyclic. So this group is not always cyclic. So how do you write it as a direct product of cyclic groups? And we'll get back to this in section 9.5, which interestingly is in the chapter on polynomial rings. So we'll sort this all out and we'll be able to write down z mod nz star as a direct product of cyclic groups.